Hey, welcome back to Abstract Algebra. In this first of 3 lectures of the material that's covered in section 4.3, we're going to take a look at an introduction to ring homomorphisms. So it's the analog of a group homomorphisms for our new object. I'm going to define the kernel of them. Ring homomorphisms, like group homomorphisms, have kernels. I'm going to define a new object called an ideal and hopefully illustrate all of these definitions with lots of examples. All right, so we'll get going. So here's the main definition. Some of this stuff I wrote out ahead of time. Some of it will work together to slow me down a little bit here, but here's the main definition. And hopefully it's not a big surprise. So if you have a function between two rings, so R and R prime are rings, I've got a function called phi between them. I'm going to call that function a ring homomorphism if for any two elements in the domain. Well, first of all, phi of a sum is the sum of the phis. So that is, phi is just an additive group homomorphism on the additive group structure underlying in this ring. And then we're also going to require phi to preserve the multiplication operation. So we need that phi of AB is phi of A times phi of B. So it's a very natural definition. A ring homomorphism is a function that preserves both operations in a ring. Here's my first remark. I already said it out loud, but among other things, a ring homomorphism is a group homomorphism. Here in this notation, I'm just writing R plus and R prime plus just to indicate that I'm focusing on the additive group structure in this ring. All right, so I'm going to just say this here, and we can talk about it in class, but everything that you know about group homomorphisms applies to ring homomorphisms as long as you're applying it to the additive group part, because ring homomorphisms are group homomorphisms and then some. Yeah? Okay, cool. Continuing, we'll make a definition here. The kernel of a ring homomorphism, this is some good news actually. The kernel of a ring homomorphism is exactly the same definition of it as if you forgot about the multiplicative part. So the kernel of a ring homomorphism is the elements in the domain that map to the additive identity. So the kernel of a ring homomorphism, it's the same set as if phi were just a map from the additive abelian group R to the additive abelian group R prime. So by this 0, I mean the additive identity in R prime. So the notion of kernel actually hasn't changed, which you might think is a little bit of a surprise, like where's the multiplicative structure in there, okay? So the kernel of a ring homomorphism is the set of elements that map to the additive identity. I'm going to highlight that to emphasize it's important. It's the additive identity, not the multiplicative identity, because I'm not even assuming these rings have unity, right? There might not even be a multiplicative identity. Okay, last definition, last new technical term. Here, I should have been doing this as we went along, but yeah, these technical terms I should have been coloring in blue. I guess I'm underlining them. So ring homomorphism, here I can color them quicker. Ring homomorphism, technical term, know it. Kernel of a ring homomorphism, technical term. Here's the last one for this lecture, an ideal. Okay, here's how we're going to define an ideal. An ideal in a ring, well, it's a non-empty subset, calling it I for ideal, and it kind of has two conditions. First of all, it's an additive subgroup. Okay, so if you look at this subset, it has to be closed under addition. It's got the 0. It's closed under inverses. It's an additive subgroup of the group R under addition. And then here is the multiplicative part. For any element in this subset and for any element in the ring, this second element does not have to come from the subset. We require both A times R and R times A to be in the subset. Okay, so this is like a closure property, but again, only one of the two elements has to come from I. The other element can be arbitrary. So you pick an element of I and an element in the ring, and those products are in I, then you call I an ideal. Here's our first result of the lecture. It's lemma 431 in your book, and it says that if you take a ring homomorphism, its kernel is an ideal. The kernel of a ring homomorphism is an ideal. It's kind of the motivating example of ideal. So let's prove this. I'm going to try to give you the spirit of that a lot of this work is done in group theory. So I'm going to start by saying, well, that we know that the kernel of phi is a subgroup of R under addition. I'm always just going to write this, as a pair when I'm emphasizing the ring is additive group structure. So we know that from the past. Yeah, that's previous work. And so in particular, the kernel of phi can't be empty. The subgroup has to have the identity element in it. So it's a non-empty, I'm just checking the definition. Got a non-empty subset so far. And yeah, it's an additive subgroup because it's a kernel. So now we're going to check this I like to call this second condition, the sticky property. Why do I call it the sticky property? Because if you take an element in the ideal and then any other element, the products have to land in the ideal. So I think of the ideal as kind of being sticky in the sense that if A is in there, anything that bumps into A is in there. You can ignore that, though. You don't have to call it the sticky property. But here I'm going to show that a kernel has the sticky property. I'm going to choose an element of the kernel, picking an element of the kernel, and then I'm going to pick an element of the ring, an arbitrary element of the ring. And then I'm wondering if A times R is in the kernel. Well, if you want to know if something is in the kernel of a ring homomorphism, take phi of it. It's a ring homomorphism, so it's multiplicative. Phi of A is 0 because A is in the kernel. And we proved that 0 times anything is 0. So that shows that AR is in the kernel. I'm going to run out of room, so I'm going to leave it to you. Similarly, I hope you'll do it. RA is also in the kernel of phi. So the kernel of phi is an ideal. It's a subgroup with the sticky property. Good. All right. I have to learn how to plan my spacing a little bit better. I don't know why I'm so worried about saving all of this electronic paper. I should just space things out as far as I can. Let's look at an example. We haven't had an example of a ring homomorphism. So fix an element n, fix a natural number, a positive integer n, and define phi from the ring of integers to the ring of integers mod n by sending an integer to its equivalence class. Okay, so I claim that that map is a ring homomorphism and its kernel is the subgroup generated by n. It's the multiples of n. Let me try to prove that claim to you. So first of all, if we take two integers, say m and k, in Z, well, we can look at phi of m plus k, and by definition of phi, that's the class containing m plus k. Addition mod n is well defined, so that class adds like this, and that's precisely phi of m plus phi of k. And if you bought that, the multiplication is going to go the exact same way. Phi of m times k, well, it's the class containing m times k. Multiplication mod n is also well defined, so that's the product of those two classes. So that's phi of m times phi of k. So that shows phi as a ring homomorphism. Preserves both products. Now let's just try to calculate the kernel. An element m is in the kernel. I'm going to do kind of a pick-a-point proof in both directions at the same time here. An element m is in the kernel if and only if, well, phi of it is the additive identity. That's the 0 class. That's if and only if the class containing m is the class containing 0, and that's if and only if m is a multiple of n. The only way you represent the 0 class is if you're a multiple of n in the integers. Yeah, good. So the kernel of that ring homomorphism is just the numbers that are divisible by the number n. Cool. Here's another little kind of, I'm calling it a proposition. You could call it a lemma. It doesn't have a number. The author doesn't mention it specifically as a numbered lemma in his book. But let's see what it says. So you take any ring, but it has a unity. Take a ring with unity, and you take an ideal in it. So this lemma says that if you have an element in your ideal that's a unit, remember a unit is an element with a multiplicative inverse, then your ideal is actually the entire ring. If a unit is in an ideal, the ideal has to be everything. Let's see why. In some sense, it's because the ideal is sticky. But let me see if I can make that more precise. So let's take the hypothesis that we've got a ring, we've got a unit, we've got an ideal, and let's suppose that A is a unit. It belongs to this ideal called I, okay? Well, if A is a unit, then its inverse is an element of R. And so if I multiply A by its inverse, I get an element of I because I is an ideal. Ideals are sticky. But the inverse of A times A is 1. So that means 1 is in the ideal. All right. But then for every element B in this ring, B is certainly 1 times B, and that's in I because I is an ideal. It's sticky. Yeah, you guys following me? The element 1 is in I, so 1 times something is in I. Well, that means that every element in the ring is in I. I mean, certainly I is a subset of the ring, and so that's the conclusion of the proof. If an ideal has a unit in it, it's everything. All right, sorry, I'm smashing this together a little bit. I'll try to make some more room next time, but as a corollary of that, fields don't have very many ideals. Remember what a field is? A field is a ring in which every non-zero element is a unit. I'm going to leave this as an exercise to you, but the zero set, the set containing only the additive identity and the entire ring, those are always ideals in a ring. So in particular, a field has those two, but this corollary says those are the only two. So to prove that, if you take a non-zero ideal, then there has to be a non-zero element in it. But that element is a unit. Every non-zero element of a field is a unit. So the previous thing says that that ideal is equal to F. Nice. I'm smashing this in a little bit too much for you guys. We can talk about it in class. As I think, yeah, a last example, and I'm going to leave a lot of this work to you, but as a last example, I want to introduce kind of a new ring. I'm going to leave the fact that it's a ring to you, but let me tell you what it is. So as a set, R is the set of functions from the unit interval into the real numbers that are continuous. All right, so think about like continuous functions from calculus, but I'm just restricting their domains to the unit interval. And their outputs are real numbers. If you define pointwise addition and multiplication of those functions, so you add two functions and multiply two functions like you did in calculus, f plus g of x is f of x plus g of x, and so on. You don't have to prove this here, but the sum and product of continuous functions are continuous. You can take that for granted. That's a fact from calculus, or if you're in the real analysis class, you've given rigorous proofs of that, but you sum two continuous functions or multiply two continuous functions, you get a continuous function. So those are really binary operations on R. And here's your exercise. Your exercise is to show that R is a commutative ring with unity under those operations. All right, so you can show that it's an abelian group. Tell me what the inverse is, what the additive identity is, show me that multiplication is associative, distributive, tell me what the multiplicative identity is. Okay, so I'm going to leave that as an exercise. But here, I'm going to take a look at a subset of this ring. I'm calling it I, suggestively, and it's those F in the ring that have the value 0 at 1/2. If you like, it's those Fs that have an x-intercept at 1/2. Yeah, so you could take the continuous function, I don't know, x minus 1/2. That's in the ring. There's lots of functions in here in this. So my claim is that this set I is an ideal. So I'm going to end this video lecture. I'm talking a mile a minute, but you can slow it down with a proof of that. So an ideal, what do we need to show? Additive subgroup and that it has the sticky property. So let's take the subgroup part first. First of all, why isn't I empty? You can use the identity, the usual suspect, but I think I'm going to use the function I just spoke out loud. If I define the function from 0 to 1 to the real numbers by saying that f of x is, say, x minus 1/2, that's continuous, yeah? And f of 1/2 is 0. So there's a function that's in I. There's lots of functions in I. The 0 function, the identity is in I. Good, so it's not empty. And now let's suppose we have two functions, say f and g in I. I want to show that f plus g is in I. Well, by definition, f plus g of 1/2 is f of 1/2 plus g of 1/2. That's 0 plus 0. 0 plus 0 is 0. So that shows that f plus g belongs to this set, I. Finally, if I look at minus f of 1/2, well, that's minus 0, which is still 0. So the additive inverse of this function is in, oops, I. So that shows that I is an additive subgroup. All right, so we just have to show the sticky property. Let's take some element A in I. Let me not call it A, sorry, it's a function. Let's take some element F in I and some element G in this ring. All right, and what do I have to do? I have to show that F times G and G times F both belong to I. Okay, well, to get into I, you have to send 1/2 to 0. So let's look at it. This isn't function composition. This is pointwise multiplication. So it's F of 1/2 times G of 1/2. And that's 0 times, well, I don't care because 0 times anything is 0. So that shows that FG is in I. To keep the video short, I'm going to say you show that GF is in I the same way. If you do, I is an ideal. Okay, so I'll just kind of wrap up one more time in this video. I'm sorry, I'm gonna watch your eyes. I'm gonna scroll fast on you. What did I do in here? I've defined some new terms for you. Some new terms that I want you to know technical, rigorous mathematical definitions of. They are ring homomorphism, kernel of a ring homomorphism, and ideal. I gave you a few examples illustrating those, and we will continue looking at them when we start looking at factor rings, and that's in the next lecture. Okay, thanks for listening.